Zig is not just another programming language. It's a powerful tool for developers who want to emphasize performance and safety in systems programming. Today, we're going to dive into the advanced features of Zig, such as compile-time code execution and optional memory safety, which set it apart from other programming languages. So far, we learned about the Zig programming language, focusing on its efficiency and safety for system-level programming. We covered fundamental concepts such as defining structs, error handling, compile-time execution, and memory management, highlighting Zig's distinct features that enhance code clarity and performance. Additionally, we explored testing capabilities and the simplicity of Zig's build system. Now we will talk about advanced topics including compile-time execution and memory safety, which can significantly elevate your code quality and performance. Now let's implement compile-time code execution through a function that calculates the factorial of a number. Here, we first define a constant n set to 10, which represents the number for which we want to calculate the factorial. Using the compute factorial function, which is declared to run at compile time, we take advantage of Zig's ability to execute code before the program runs. This recursive function checks if the input n is 0, returning 1, which is the base case for factorial. Otherwise, it recursively multiplies n by the factorial of n1. Now let's see how we can utilize this functionality in the main function. Here, we print the result using std debug print, displaying the factorial of n. Since the factorial is computed at compile time, the runtime overhead is minimized, allowing for efficient execution. This technique is particularly useful in performance-critical applications where constant values can be pre-computed, further showcasing Zig's strength in systems programming by enabling developers to write optimized and clear code without sacrificing performance. Now let's see how we can implement optional memory safety in Zig through the use of the optional type. In the provided code, the function getValue is designed to simulate a scenario where it may or may not return a valid integer. The introduction of randomness via std-rand, default PRNG, next, creates a 50-50 chance to either return a valid integer value or null, thus demonstrating the optional nature of the return type, represented as I32. Within the main function, we invoke getValue and use a switch statement to handle the return value safely. This structure enables the program to perform different actions depending on whether the value is null or holds a valid integer. If the value is null, the output will convey that no value is present, highlighting how optional types help in preventing null pointer exceptions. Conversely, if a valid integer is returned, it displays that value. This approach not only enhances code clarity but also explicitly communicates the programmer's intent, significantly reducing the likelihood of runtime errors related to null values. This example illustrates the power of Zig's optional types in writing safer and more reliable code. Now let's explore how Zig handles dynamic memory allocation by implementing a simple example to allocate and manage an array. We begin by utilizing Zig's standard library to access the page allocator, which is designed for allocating pages of memory efficiently. Next, we specify the size of our array, 5u32 integers, and use the allocator's alloc function to request this memory. If the allocation fails, Zig's error handling mechanism catches the error, allowing us to print a message and exit gracefully, ensuring our program doesn't crash unexpectedly. Now let's populate the allocated array with values. A loop iterates over the array, assigning each index a value that doubles its position. This demonstrates how you can manipulate allocated memory directly and clearly, adhering to Zig's explicit nature of memory management. Once the array is filled, we output its contents to the console, showcasing the values stored. Finally, to maintain good memory hygiene, we explicitly free the allocated memory using the allocator's free method, reinforcing the importance of manual memory management in Zig while ensuring that we do so safely and efficiently. Now let's see how we can implement a straightforward error handling mechanism using Zig's approach to division. In this example, we define an error type that includes a division by zero error to indicate the specific issue that can occur when dividing by zero. The function divide takes two floating point numbers, x and y, and if y is detected to be 0, it returns the division by zero error instead of allowing a runtime fault. This makes our function more predictable and easier to debug. In the main function, we call the divide function with a deliberate attempt to divide 10 by 0, which we know is invalid. The result from this function call is captured in a variable named result, and we utilize a switch statement to handle various outcomes. If the function returns the division by zero error, a clear error message is printed to the console, informing the user of the attempted illegal operation. Alternatively, if the division is successful, the result is printed. This method not only enhances the visibility of errors but also improves maintainability within your code by clearly delineating paths for handling different scenarios. Now let's take a look at how we can implement compile-time testing in Zig, which enhances the reliability of our code. In this example, we define a simple function called add that takes two unsigned 32-bit integers as parameters and returns their sum. Next, we create a test case using the test keyword, which automatically runs during the compilation process. Inside this test case, we call the add function with the values 2 and 3. We then use Zig's built-in testing feature, std testing expect, to assert that the result equals 5, which is what we expect from adding those two numbers. If the result does not match the expected value, the Zig compiler will raise an error, informing us that something went wrong. This approach to testing is particularly beneficial because it allows developers to maintain code integrity without requiring a separate testing framework, thus streamlining the development process. By incorporating compile-time testing, we ensure that our functions behave as intended as we develop, contributing significantly to the overall safety and reliability of our code. The combination of compile-time constant evaluation, explicit memory management, and robust error handling makes Zig a unique and compelling choice for developers seeking to build software with fewer surprises. Isn't that right? It's like having a well-organized toolbox. You know exactly where everything is and how to use it without undue complexity or overhead. In conclusion, Zig provides powerful features that greatly enhance not only performance, but also the reliability of the code you develop. The compile-time execution enables you to compute values ahead of time, while optional memory safety allows for expressively safe programming without sacrificing performance. Zig's explicit memory management and its innovative error handling system encourage users to write clear, maintainable code. So, as we've seen in today's lesson, Zig combines safety with performance in a way that should excite any systems programmer. Next time, we will dive into concurrency and task management in Zig, exploring how to leverage these powerful tools to build efficient and responsive applications. Thank you for joining me, and I look forward to seeing you in the next lesson.